Today's video will be on lesson 4.14, which is on Newton's law of cooling. Now you do not actually have to know Newton's law of cooling. We are just using it in this unit because it deals with variables being in the exponent spot, which we are going to need logs to solve for. So while you do not have to memorize what his law says, you just have to know how to work with it. So if they ever did ask you a question on Newton's law of cooling, they will give you the formula and you have to just know which numbers to plug in for which variables and how to solve for whatever's missing. It's usually going to be the exponent where t is. So just a little background, Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature, or the temperature of its surroundings. So we're just going to look at one example and work through how we would actually use logs to solve for something in science. So exercise number 3 says, let's stick with the same cooling liquid that we had before. And I think this was in one of the previous videos. i.e., it's one that starts at 200 and cools down in a room that is held at a constant temperature of 70 degrees. We will now model this cooling Fahrenheit temperature using this equation. F of t equals A times B to the t plus C, where A, B, and C are all parameters or constants in the model, and t is the time in minutes. So part A says, which of these constants is equal to 70 and why? So 70 in this equation is going to be your C. And that is because it is constant and it doesn't change. No matter what temperature the liquid is, it will not change because 70 is the temperature of the room. The room is held at a constant temperature. It's not going to go up, it's not going to go down, no matter what we do to this liquid. The temperature of the room is going to be 70. So 70 is constant, it won't change. Part B says, none of these constants is equal to 200, but t of 0 equals 200. What constant does this let you solve for? And then find its value. So 0 is in the inputs spot. So that means I'm going to input 0 in for t. So I'm going to have, and by the way, 200 is the output. So I should clarify that because I'm going to start with that. So I get 200 when I input 0. So I know what I get 200. When I input 0, well, I don't know what A is. I don't quite know what B is, but I actually do once I plug in 0 for t. And C is 70. That's your constant temperature of your room. Well, at first glance, it looks like I don't know A or B, but you know that anything to the 0 power is 1. So this turns out to be 200 equals A times 1, which is just A, plus 70. Now you can solve for A. So the question says, what constant does this let you solve for? It lets you solve for A, because B to the 0 is 1. So now if you subtract 70 over to the other side, you get 130 equals A to the first. And that's your answer. Part C, in order to find the value of B, what additional information would we need? So to find B, you would need a point, any point that they give you, and the point would represent time and temperature. So your x value, so to say, in your point would be the time, and your y value would be the temperature. If you know a point, you can plug those in to find your B. So that is what they did in part D. It says determine the value of B if the temperature after 5 minutes is 153 degrees Fahrenheit. And you're going to round to the nearest hundredth. So we know our answer, our output is 153. This is your y, so to say, and this is your x. So if I plug those in, I get 153 equals 130 times b to the 5th plus 70. And recall I got the 130 up here in part B. That's what your A is. Now you can solve for B. So we're going to subtract the 70 over to the other side, and that's 83 equals 130 times b to the 5th, and then divide the 130 over, and I'm going to leave it as 83 over 130. I'm not going to write it as a decimal. Leave it as a fraction. Equals b to the 5th, and now you fifth root both sides, and this is where you'll use your calculator. Fifth root 83 over 130. It says round to the nearest hundredth. B turns out to be 0.91 for that particular data point. Part E says, what is the temperature of the liquid after half an hour? So half an hour is 30 minutes. And then it says after 1 hour, that's 60 minutes. After 2 hours, that's 120 minutes. You're just going to plug those in. So after half an hour, that's 30 minutes. And it has to be in minutes because that's what our time in our formula was given as. An hour was 60 minutes. 2 hours is 120 minutes. So you're just going to plug those in for your T. So we have 130. We found our B to be 0.91. Raised to the 30th, that's the number you're plugging in for your time, plus 70. If you type all of that into your calculator, you get, it doesn't say what to round to, does it? Okay, so I'm just going to write 77.677. That's what the temperature would be. Again, you're going to do this because now we know our A, our B, and our C, so we can plug in any time we want. And now they asked us to evaluate it after 1 hour. That's 60 minutes. So that is 70.453. Now, if you use your common sense, that should make sense that the temperature went down as time goes on. Your liquid's going to get cooler. And lastly, they asked for 2 hours, which is 120 minutes, plus 70. It should be even less. Your temperature should have dropped. It's going to be 70.002. Now, you should notice the temperature is going to get closer and closer to 70 because that's the temperature of the room, right? Your liquid won't get colder than what the room temperature is. So now it says for part F, using your calculator, sketch the graph of the liquid's temperature. Well, I just told you 70 is the room temperature. I'm going to dot this line here, and that is what my liquid is attempting to get to. And if you recall, it started at 200. So it's going to be an exponential graph because it is going to drop rapidly, but then level out and try to get to 70. It eventually will, but we don't know how long that will take. So you're going to do an asymptote at 70. And let's see, algebraically determine to the nearest tenth of the minute when will the temperature reach 100 degrees. So remember, it started off at 200. How long will it take to get to 100? So I know my output is 100 because that's what I want to get to. My equation, I solved for A, B, and C. A was 130. B was 0.91. I don't know how long it'll take, so that's T. And then plus 70. So now I'm just going to solve. And notice, look at here, T is the exponent. So I'm going to have to eventually log both sides in order to get T to drop down. But remember, before you can log both sides, you need to get what is directly connected to the exponent, which is only the 0.91. We'll box it in red. The only thing that's being raised to the T is 0.91. So I want to get the 0.91 alone. So first we're going to move the 70 over to the other side by subtracting 70. So I get 30 equals 130 times 0.91 to the T. And now I need to move the 130 over by dividing it because it is multiplied with the 0.91. Again, I'm going to leave it as 30 over 130. So I will rewrite this, 30 over 130 equals, and I'm going to leave a space here so I don't have to rewrite this again, 0.91 to the T. Now I left a space because I'm going to log both sides to get the t to drop down. As soon as I log both sides, and I'm going to leave it as 30 over 130, but I'm going to put parentheses around it. As soon as I log both sides, the t can come down, and I'm left with the log of 0.91. Now I can divide the log of 0.91. Remember, you can't separate a log with the word log with the number that's next to it. It is one number. It stays with the word log. And from here, you'll use your calculator. Just make sure you type it in correctly. Make sure 30 divided by 130 is in the same parentheses with the first log, and then divided by the log of 0.91. T turns out to be about 15. It says nearest tenth, so 15 and a half minutes, 15.5. And that is it for this example. Notice you don't have to understand Newton's law of cooling, but we did need to use logs to solve for how long it would take until we reached 100 degrees. So science uses math a lot in their formulas and solving. And that is it for lesson 14.4.